Hello, this is Zeph Smith, and I will be doing this review of Math 1060, that's trigonometry, the fall final exam from Salt Lake Community College, version 2, fall 2013. This exam has two parts, and any calculator is allowed for the most part, but not on part 1. You must complete part 1 without using a calculator and show all appropriate work, clearly indicate your answers, etc. Then you turn that in and get your second part where you can use a calculator. Okay, and it is not necessary to rationalize denominators. That's always nice. You don't have to worry about that. Let's get started on part 1. Number 1, given that sine alpha equals 1/4 and alpha is an angle in quadrant 2, find the exact values of all the remaining trig functions. What I always do on these is draw the triangle. Sine alpha equals 1/4. Alpha, any angle, can be represented as a triangle. So, and I'm going to do quadrant 2 angle. So this, from this center, the origin, out into quadrant 2 and straight down right triangle. This, if that's alpha, then sine is opposite over adjacent. That's what sine is. So sine would be 1 there and 4 there. Now the hypotenuse is always positive, so this is positive 4. This direction is up 1. Up is positive, so that's a positive 1. Now we have 4 as the hypotenuse, we have 1 as one of the legs, and we can solve for the second leg with Pythagorean theorem. And for this first one I'll write it out. For the rest of the test I might not. But a squared plus 1 squared equals 4 squared, giving us a squared plus 1 equals 16, a squared equals 15. So a is the square root of 15. However, it's negative. The reason why it's negative is this distance is left, and that's the negative direction. Now that we have our triangle for alpha, cosine, tangent, cosecant, secant, cotangent, those should be pretty easy knowing SOHCAHTOA, which I'll write down as well. SOHCAHTOA. Nice way to remember that sine is opposite over hypotenuse. That's 1/4. We already know that. Cosine is adjacent over hypotenuse. That would be this. So we can write down cosine. It's negative square root 15 over 4. And tangent is opposite over adjacent. This would be 1 over negative square root 15. And we were already told that we don't have to rationalize the denominator, so these are fine. You can put the negative on the top with the 1 if you'd rather, or simplify if you want. Now cosecant, I don't even have to look at the triangle for cosecant. Cosecant's reciprocal of sine, so that would be 4 over 1. Secant's reciprocal of cosine, so that would be 4 over negative square root of 15. And cotangent's reciprocal of tangent, so that's negative square root of 15 over 1. Now you can think, oh, I can simplify, I can put this negative here or there, I can rationalize denominators, but you can also say these are all correct. And that's it. That's the end of this problem. Next one. Find the exact value of each expression. If the expression is undefined, state so. Alright, so cosecant. I'm going to be thinking sine. And then I'll take my answer and flip it. This angle, it's pi thirds reference angle. Any thirds, pi something thirds, 2 pi thirds, 5 pi thirds, 7 pi thirds, that's all pi thirds reference angle. And 5 pi thirds is in quadrant 4. Where sine, so now I'm going to do, let's see, how do I want to do it? Let's see. Okay, let's do it this way. So sine of 5 pi thirds is going to be, sine of pi thirds is square root of 3 over 2. But in quadrant 4, sine is negative. Where that comes from is a simple all students take calculus. This tells us that all sine, tangent, cosine are positive in quadrant 1. Whereas in quadrant 2, only the sine is positive. In quadrant 3, only the tangent is positive. And in quadrant 4, where we are, specifically 5 pi thirds is right here. 5 5 pi thirds. Only cosine's positive. We're doing secant, cosecant, which is 1 over sine, which will be negative. So that's why we have our negative. Now our final answer, since we're doing cosecant, is flipped. So you take our sine and flip it. All right, cotangent. I'm going to think tangent. All right, now first off, where is this? Negative pi 6 is right here. So again, we're quadrant 4 and pi 6 the reference angle. I can do cotangent directly. Cotangent x is cosine x over sine x. So cotangent, looks like I'm going to need a little more space on this problem. Cotangent, cosine of pi sixths is square root 3 over 2. In fourth quadrant, cosine is positive. Cotangent, cosine over sine. Sine of pi 6 is 1/2, but in quadrant 4, it's negative. We invert and multiply these, and we get negative square root of 3. That's cotangent. All right, secant. First off, 450 is outside the first circle. So we take 450 and we subtract 360. And we get 90. So secant of 450 equals secant of 90. Just subtract 360. This is a coterminal angle, so they're equal values. Secant 90, this is 1 over cosine of 90. Cosine of 90. Cosine starts at the amplitude and hits 0 at 90 and goes on through its cycle. This is 1 over 0. This is undefined. Okay, so we have 3 values. Obviously on the test you're going to be able to write smaller with this iPad. I'm having to write with this little stylus, and it just takes a lot of room to make it look good. So, but still, having these 3 with the boxes around them makes your teacher easily be able to look at your answers and then go, okay, that's correct. If you don't have a box around it, it forces your teacher to look through all of your work. And even if you got the right answer by the wrong means, you might have still gotten credit for it if I could have seen it. But instead, I'm going to look through all your work and find any mistakes you might have made. So, just as a warning, make sure your answers are easy to spot. Next question. Arc functions. The exact value. All arc functions, sine, cosine, secant, cotangent, cosecant, tangent, all of them only have one answer. So for arc sine lives either in quadrant 1 or quadrant 2. Sorry, I said quadrant 2. Quadrant 1 or quadrant -1. If the value that you put into arc sine is negative, we will get something in the negative quadrant 1. So now we ask ourselves, when is sine 1/2? And that's 30 degrees. So this is the value. Negative pi sixths. Oh, I put a degree sign. That's funny. I'll erase that. Negative pi 6 or negative 30 degrees. Since they asked for radians, our answer is negative pi 6. Arc secant. So we want to think, I would do this. First off, that's arc cosine of 1/2. That's how to convert from arc secant to arc cosine, is flip the inside. Arc cosine lives here or here. That's where arc cosine lives. And where arc cosine is positive is in quadrant 1. Well, that's also where arc secant is positive. So we're in quadrant 1. We're somewhere in here. Where's cosine 1/2? 60 degrees, or pi thirds. That's where cosine would be 1/2. That's where secant would be 2. All right, last one in this one, arctangent. So arctangent lives the same spot arcsine does. So we are going to be in negative quadrant 1 because we have a negative number. Now there are two basic values that we need to concern ourselves with. That would be negative pi sixths or negative pi thirds. Both of them will have the square root of 3 involved. So just briefly, tangent pi sixths would be sine pi sixths over cosine pi sixths. That's 1/2 over square root of 3 over 2. That's 1 over square root of 3, which we can rationalize, although they said we didn't have to for this problem. There we go. That's the value we have. We have the one where tangent is square root of 3 over 3. That's the pi sixth version. Now we know that we're in the negative quadrant 1 because that's where arctangent lives. So let's put a box around that. So our answers for this problem, we have negative pi sixths, we have positive pi thirds, and we have again negative pi sixths. All right, next question. Sketch the graph. Sine wave, negative 3 pi x minus 1. Sketch at least one full cycle. Clearly label the 5 key points. Okay, the x-intercepts and the points corresponding to the maximum and minima, those would be the 5 key points. So let's get some basic information. Amplitude. Wow. Let's try a pen this time. Amplitude. There we go. It's going to be 3. But go down first because of the negative. Period. The period is the normal period of 2 pi divided by the coefficient of x. So we get a period of 2. So it's 2 pi divided by this guy. Alright, phase shift. This one is right 1 because of this minus 1 in there. You can ask yourself, what makes this 0? Whatever value makes that 0 is the phase shift. Okay, I'm going to put in red, first off, where our normal, so this will be, let me write this down, y equals negative 3 sine pi x. That'll be the red one. I'm going to graph that one first, but just dots, maybe x's, something. So sine normally starts at 0. The period is 2, so after a full period of 2, it'll be back to 0. Halfway in between, it'll be at 0. Now the sine usually goes up, but we've already determined that this one's going down because of this negative sign. So it goes down to the amplitude. And now with this 1 and this 2, that's going to be pretty extreme. Maybe I'll make the y values a little bit different. Just going to get to there and to there. So you can see the sine wave. We're asked to sketch at least one full cycle, so this is all we really need to do. But we still haven't accounted for the phase shift. So now in a different color, I'll use black. I'm going to go right 1. This old point is going to go right 1. This point's going to go right 1. This point, right 1. Right 1. I'm missing something. I'm going to have to redo those. Let's see if it will let me undo. No, of course not. Oh, it erased just fine. Let me try this again. Where is right 1? So, this point is going to go right 1. I was going right half by mistake. Right 1 is over here. This point's going to go, it's at a half. It's going to go right 1, so it's going to be at 1.5. This one's going to go right 1. Right 1, right 1. Okay, so, oh, wrong color. Try that again. Go Oh, that one's right one, that right one, that right one, that right one, that right one. So this point going right one, this point right one, this point right one, this point right one, this point right one. And we finally end up with this one cycle. Now it says clearly label the 5 key points. I'm going to expand this graph a little bit. There we go. This would be 1 comma 0. This would be 1.5 comma negative 3. Then we have 2 comma 0 and 2.5 comma 3 and 3 comma 0. That would be labeling the 3 key points. The 5 key points. These are the 5 key points that correspond to the x-intercepts, 1, 2, 3, and the maxima or minima, minimum, maximum. So the way I like to graph these is I like to graph everything except for the phase shift and get those down, and then phase shift it, whether it goes up so far or whatever, right, left, and then phase shift each point. You might have another way. Whatever way you're comfortable with, obviously you want to be reviewing that if it's consistent and correct. Let's move on to the next one. Sketch the graph of cotangent. Okay, I'm going to do the same thing. First off, amplitude, there isn't really an amplitude, but we do have the 1 out in front. The period is the regular period, which is pi. Tangent and cotangent have regular period. And it would be pi divided by the coefficient of the x, which is 1, so that no change to the period. And we have the phase shift. That would be left pi fourths. You'd be asking yourself questions like, what makes that 0? Left pi fourths. Okay, so in red I'm going to do the unshifted one. Normally, the cotangent starts on an amplitude, and then after a period of pi, it has an amplitude again. And halfway in between there, it's at its 0, and then it would be going down like this. Cotangent's a decreasing function. You can have cotangents be increasing, but you'd need a negative amplitude to flip it around. Sketch at least one full cycle. This will do it. But we have to go left pi fourths. So the old amplitude of 0 is now going to be left pi fourths. There we go. This old amplitude at pi is now left pi fourths as well. And this center point left pi fourths. Let's see, this is pi, pi half, so pi fourths would be about there. And now we can sketch this decreasing function in between the amplitudes. In between the asymptotes. Get this right? Alright. Now it says accurately label any asymptotes and x-intercepts. Alright, this would be x equals negative pi fourths. This would be x equals 3 pi fourths. This would be, let's see, that would be pi fourths comma 0. To explain how I get those, it used to be pi, this asymptote, and I went left pi fourths, so if you take pi minus pi fourths, you get 3 pi fourths. This used to be pi halves comma 0, and we went left pi fourths, and now it's pi fourths comma 0. And this asymptote was 0, and left pi fourths is minus pi fourths. Now the equation of all vertical asymptotes, so we only have 2 of the infinite number. We can take either one that we have, let's say x equals 3 pi fourths, the first positive one, and add a general period. Period is pi, so I'd add k pi. And that would get us this, plus a period the next one, plus a period the next one, etc., plus a negative period this one, etc., and that'll give us all the asymptotes. For cotangent and tangent, the general formula for all vertical asymptotes is x equals the first positive asymptote that you have plus k times the period of the graph you're working with. You also want to make sure to tell people what k stands for. So k and integer. There we go. And this problem is complete. Prove that the following equation is an identity. Now, as I look through this problem, on the right side I see a cotangent. I see two terms. On the left side I see one term and a bunch of sines and cosines. I like cosines and sines. So, let's see, I see something else. There's a 1 minus cosine squared. That one kind of sticks out. Now, sure, it's not written the normal way, but if we wrote this, the left side, cosine x plus 1 minus cosine squared x all over sine x, all I've done is just rearrange these two terms. It gives me this piece. That's a fundamental Pythagorean identity. That's sine squared right there. Now you have to have 1 minus cosine squared. The squared's critical. You cannot replace a 1 minus cosine with a sine. But 1 minus cosine squared you can. So this is cosine x plus sine squared x all over sine x. Okay, we can then split this up into two fractions. Cosine x over sine x and sine squared x over sine x. And then that simplifies. Cosine over sine is cotangent, and one of these signs cancel, and that's sine, and we've shown the identity. We worked the left side until it was equal to the right side. I would probably, on my own, have an equals here to finish the job instead of an arrow. But I ran out of space and just wanted to be cute about it. But now it's a nice, complete, full identity. I'm sure there's about 5,000 other ways to do this problem. That's just the way that I saw to do it. Okay, next one. Find the exact value of the following expression. Simplify your answer. Hint, you will need to use an identity. Now, the 2 sine squared minus 1 looks like an identity that you probably know. I hope you do at least. Cosine 2 theta equals 1 minus 2 sine squared theta. This isn't exactly what we have. We have the 2 sine squared angle minus 1. So we have to manipulate this a little bit. If we just multiply both sides by -1, we will get minus cosine 2 theta equals, and when we distribute this negative, this first one will turn into plus. We'll put that one first. 2 sine squared theta, and then minus 1. This is what we need. Okay, here's our formula. 2 sine squared some angle minus 1. 2 sine squared some angle minus 1. In this case, that some angle, theta, equals pi eighths. Great, great, great. We actually need to evaluate it 2 theta. So let's work out 2 theta as well. 2 theta equals pi fourths. You can get that just by multiplying both sides by 2 and reducing it right there. Okay, so we now know 2 theta. So we really want to work out minus cosine 2 theta. That is minus cosine pi fourths. That's minus square root of 2 over 2. And we have the exact value, no calculator stuff, of course. Perfect. We are complete. Find the exact value. Cosine alpha minus pi thirds. If sine alpha equals 1/3 with alpha in quadrant 2. Well, this sine alpha equals 1/3, alpha in quadrant 2, I can immediately set up a triangle for that. Alpha sine is 1/3. Pythagorean theorem gives me 9 minus 1 is 8. Square root of 8, and it's negative, so -2 square root of 2. There's alpha. We might need that for when we use an identity on this cosine alpha minus pi thirds. Okay, so cosine alpha minus beta is cosine alpha cosine beta plus sine alpha sine beta. This is the difference angle for cosine identity. In our case, we'd have cosine of alpha minus pi thirds. That would be cosine alpha cosine pi thirds plus sine alpha sine pi thirds. Okay, cosine alpha cosine pi thirds plus sine alpha sine pi thirds is going to be equal to, we are now evaluating, and so we don't need sines and cosines anymore unless we don't know what they equal. Cosine alpha, we go to alpha and we do cosine of alpha, which is adjacent over hypotenuse, and we can replace cosine alpha with negative 2 square root 2 over 3. Warning, I see this a lot writing the cosine still. I don't know where that comes from, but the cosine's already done because we've evaluated the cosine. It's done. That's slow, but whatever. Okay, good. See if I can. Nope, can't delete it any faster. Okay, moving on. Cosine pi thirds, that's 1/2. It's not cosine 1/2, it's just 1/2. Sine alpha is 1/3. That was given, but you can also do opposite over hypotenuse. Sine pi thirds is square root of 3 over 2. So unit circle values. So we get equal to, I would probably write this all minus 2 square root of 2 over 6. That reduces plus square root of 3 over 6. But if you don't reduce it, you can write it all over 6. I'll probably write the square root of 3 first and then the minus because it looks good. That's the exact value in the most common form I recognize. Okay, no calculator, so we didn't need it. Next question. X's in radians, find all real numbers. Important that it says find all real numbers in radians. So this is going to be like plus 2k pi kind of a problem. Starting off with our equation, we need to solve for the trig function. So that'll include some adding stuff and some dividing by stuff, etc. So add square root of 3 to both sides. Gives us 2 sine 2x equals square root of 3. Then dividing by 2 on both sides to reduce that leaves us sine 2x equals square root of 3 over 2. Okay, great. Where does sine equal square root of 3 over 2? All students take calculus. Sine is square root of 3 over 2 at 60-degree angles, or pi thirds. So this is one answer, pi thirds. And the other one's in the second quadrant. That would be 2 pi thirds. Both of these spots, because all students take calculus, reminder, they're positive. So sine will equal square root of 3 over 2. So I want to create a general pattern to add up all of these values, all solutions. What I can do is I can take this value, pi thirds, so I'd have 2x equals pi thirds, and then I'm going to have to add full 360 or 2 pi to get to another of these answers. Add 2 pi, add 2 pi, add 2 pi. We just keep getting this answer over and over and over. So that would be plus 2k pi, comma. We also need this answer, 2 pi thirds. But we also need to add a full pi, 2 pi to that, plus 2 pi, plus 2 pi, to get all of those forever. Because we need all real solutions, not just the ones around the first time around the circle. So that would also be plus 2k pi. 2 pi k. Okay, good. I usually say 2k pi, but I said it and my hand had another idea. These are correct. However, this is for 2x. So we now have to solve for x by multiplying by 1/2 all the way through here. Make a little space. And this would be x equals pi sixths plus k pi, comma, pi thirds plus k pi. Because what we have when we divide by 2 is some stuff reduces, leaving us this remaining answer. With this answer, we want to again make sure that we label what k is for people. So, comma, k and integer. And we have our final solution. These are the solutions, all of the solutions around infinite number around times a circle that satisfy this equation. Let's move on. We are now into part 2. At this point in time, you've delivered your final to whoever's proctoring your final, and they've given you the second part of the final. In this case, you have a non-computer algebra system calculator is allowed, so like the TI-84 or just scientific calculators. These are allowed. You have to show all of your work for full credit. Number 10, a bicycle wheel with a 28-inch diameter is making 170 revolutions per minute. Okay, fine. Any kind of circle diameter revolutions per minute problem is always about the circumference. So at least one big piece is about the circumference. So I'm going to expand this a bit so I can write small here. C equals 2 pi r, or C equals pi d. These are both formulas for the circumference of a circle. Okay, now circumference is 1 revolution. That's what circumference is, 1 revolution. In 1 revolution, you'll have gone 1 time around the circle. You'll have covered a circumference worth of distance. And pi d, in this case, we have 28 for d. So this would be pi 28, 28 pi inches. This is the conversion factor that we will need somewhere along the line. 1 revolution could also be 2 pi radians, same information, is 28 pi inches for this specific circle. Critical conversion factor. Okay, now let's shrink this back to size. Move it around. Okay, we can still see it all. Great. What is the angular velocity in radians per hour for a point on the tire? Please show your work and give it an exact answer. Do not give a decimal approximation. Include units with your answer. Alright, so we start off with 170 revolutions per minute. We know, let's see, what's 1 revolution? 1 revolution is 2 pi radians. That's just converting from revolutions to radians. We are now in radians per minute. Very close. We need radians per hour. So we need to convert 60 minutes, 1 hour. We are now in radians per hour. And do not give a decimal approximation. So we're not going to use 3.14 for pi, but we still need to take the 170 and the 2 and 60 and multiply those together. And it gives us 20400. So we have equals 20400 pi radians per hour. Okay? Next up. What is the linear velocity? Miles per hour. Okay. So we can start from scratch, or we can start from our previous answer. Doesn't really matter. But what we will need for sure is 1 revolution, or 2 pi radians, equals 28 pi inches. This is how we go from revolutions or radians, times around a circle, to actual distance. Sure, it's inches, but we can go from inches to eventually miles with this nice conversion factor stuff they've given us. Let me start at the very beginning. Doesn't really matter. So we started with 170 revolutions per minute. Now, 1 revolution, instead of 2 pi radians, we can use 28 pi inches. This is where our circumference information came into play. Okay, keep track. Where are we? We are in inches per minute. Well, it's getting better. Let's get to, from inches, 12 inches in 1 foot. We are now in feet per minute. Better. 5,280 feet. 1 mile. Feet. We are now in miles per minute. Finally, 60 minutes in 1 hour, and we are in miles per hour. The conversion factor for the feet, again, that's given. You won't need to know it. All the rest you'll need to know. So now we multiply all the numbers on the top except for the pi and all the numbers on the bottom. Oh, now hold on. This one says round the answer to the nearest tenth. So this time we want a decimal approximation. So we're going to use 3.14. Actually, we're going to use the pi button on our calculator. We're going to multiply all this together. So on my calculator, I would have 170 times 28 times the pi button times 60 equals, oh, huge, 897,238 point. Then divide by 12 and I'd hit equals, and then divide by 5280 and I'd hit equals, and now I'm looking at 14.16 or 14.2. 14.2 miles per hour. Okay, so the key to this problem, the first one, that's pretty simple. It's just conversion factors, knowing 1 revolution is 2 pi radians. But when we want to go from circular, angular, or revolutions, when we want to get to distance, we must use this. C equals 2 pi r, or C equals pi d. That gets us to from revolutions and radians to 28 pi inches. I just said that gets us. I think I'm down in southern Utah right now, and I think the accent's starting to creep into my bones. All right, let's continue on.